A disperse system is a binary arrangement. It consists of a discrete component, known as the dispersed phase, distributed uniformly throughout a second component, the continuous phase. These systems span a vast physical scale. On the smallest end, you have true colloidal dispersions, like surfactant micelles, measuring between 1 nanometer and 1 micrometer. Scale up past 1 micrometer, and you reach coarse dispersions, like pharmaceutical suspensions and aerosols. But physical scale aside, every dispersed system shares a core problem: thermodynamic instability. The subdivision of the dispersed phase creates a massive total surface area. That surface area generates a high interfacial free energy. Because nature prefers minimum energy, the system possesses a spontaneous drive to separate into distinct layers to minimize its surface free energy. To prevent phase separation, we have to engineer physical interactions that counteract the thermodynamic drive. We manipulate forces of interaction between the particles, specifically the electrical double layer, van der Waals attraction, and steric repulsion. The rigid structure of a gel, the solvent capacity of a micelle, and the shelf life of an emulsion or foam all depend entirely on how precisely these interfacial forces are engineered. Gels achieve rigidity while being composed almost entirely of liquid. They are interlaced solid networks interpenetrated by a liquid medium. Often, a tiny volume of disperse phase, sometimes as little as 1%, is enough to lock the continuous phase into a semi-solid state. In lyophobic gels, like those formed by clays, the particles are held together by relatively weak forces. The particles are flat plates. Due to their specific atomic structures, the flat face of the plate carries a negative charge, while the edge carries a positive charge. The electrostatic attraction builds a highly specific geometry known as a card-house flock. If mechanically sheared, the weak bonds break and the network fluidizers into a sol. Once shaking stops, attraction resumes and the gel reforms. Lyophilic gels operate on entirely different bonding principles. Type 1 lyophilic gels form irreversible, three-dimensional networks. Rather than relying on weak electrostatic geometry, the macromolecules are locked together by stable covalent bonds. The resulting network can swell with water to fill a specific volume, but it cannot dissolve. Type 2 lyophilic gels are also three-dimensional networks, but they rely on weaker intermolecular interactions, such as hydrogen bonds. Because these bonds are weaker, type 2 gels are heat reversible, meaning they transition between a sol and a gel depending on the temperature. Certain amphiphilic block copolymers possess an unusual property. Water becomes a poorer solvent for them as temperature rises. When you heat an aqueous solution of these polymers, they form an increasing number of micelles. If the solution is concentrated enough, the growing volume of micelles will pack so closely together that movement is entirely prevented, freezing the fluid into a rigid cubic gel face. Whether utilizing precise edge-to-face electrostatic geometry or building rigid, covalently cross-linked polymer networks, gel stability requires a structural matrix capable of restricting the movement of the continuous liquid phase. To manipulate the interfacial tension between two phases, we use surface-active agents, or surfactants. These compounds are defined by amphiphility, the presence of two distinct regions in a single molecule: a hydrophilic, water-liking region, and a hydrophobic, water-hating region. Surfactants are classified according to the nature of their hydrophilic head group. They can be anionic, containing a negatively charged group, cationic, carrying a positive charge, zwitterionic, possessing both, or non-ionic, where the hydrophilic region is uncharged. When the hydrophobic tails of these molecules are introduced to water, the water molecules are forced to form rigid, structured clusters around them. The system strongly resists this. The tails aggregate together to minimize their contact with water, disrupting that rigid, ice-like structure. This massive increase in the entropy of the water molecules accounts for roughly 90 to 95% of the total free energy decrease driving the entire process. This is the hydrophobic effect. As you add more surfactant to a solution, the molecules initially orient themselves at the surface, lowering the surface tension. Eventually, that surface layer saturates. At a specific threshold known as the critical micelle concentration, or CMC, the added surfactant molecules begin spontaneously aggregating into spherical structures called micelles. This graph plots bulk solution properties, like surface tension, osmotic pressure, and solubility, against surfactant concentration. Notice the sudden change in slope on every single curve. These distinct physical pivots occur exactly at the CMC. Within an ionic micelle, the hydrophobic chains form an interior core, with properties similar to liquid hydrocarbon. Surrounding this core is the stern layer, a compact zone containing the charged head groups and strongly bound counterions. Beyond that lies the Goy-Chapman electrical double layer. Non-ionic micelles lack these layers. Instead, their core is surrounded by a shell of oxyethylene chains, called the palisade layer, which entraps surrounding water molecules. The geometry of these micelles is determined by the critical packing parameter, a ratio of the hydrocarbon chain volume to the area of the head group and the chain length. When that ratio is less than or equal to 1/3, the resulting geometry is strictly spherical. Micellization is not random clustering. It is a mathematically predictable, entropy-driven mechanism that rapidly organizes molecular structures to maintain the minimum possible free energy state. Because the interior core of a micelle acts like a liquid hydrocarbon, it can dissolve materials that are otherwise completely insoluble in water. This process is called solubilization. The exact location where a drug solubilizes depends strictly on its chemical polarity. Nonpolar compounds dissolve deeply within the hydrocarbon core. Amphipathic molecules orient at the surface among the charged head groups. Polar molecules solubilize entirely within the water-entrapping polyoxyethylene shell. This creates unique formulation opportunities. Phenolic disinfectants form clear solutions. Iodine is stabilized in iodophores, and vulnerable drugs are physically shielded from hydrolysis by the repulsive charge of the micellar surface. By utilizing solubilization, micelles function as isolated, highly engineered solvent environments suspended within the aqueous bulk, providing critical stability to chemically vulnerable compounds. In coarse disperse systems, like pharmaceutical suspensions, the physical parameters change. The insoluble particles exceed 1 micrometer in diameter. Because of their size and mass, they are directly subject to gravitational settling. This chart displays a standard DLVO potential energy curve. It plots the interaction energy between two approaching particles against their distance. If the electrical repulsive forces are overcome, particles fall into the deep primary minimum. In a suspension, gravitational forces pack settling particles tightly together at the bottom of a container. Once they enter this primary minimum, physical bridging and crystal growth lock them into a hard, irreversible cake that cannot be shaken apart. To prevent caking, we induce controlled flocculation. By adding electrolytes, we suppress the zeta potential and shrink the repulsive energy barrier. This shifts the entire DLVO plot downward, creating a deep enough secondary minimum to trap the approaching particles before they reach the primary minimum. Here, they form a loose, bulky structure called a flock. The particles sediment, but because they are loosely bonded, they easily resuspend upon agitation. Suspensions can also be sterically stabilized. The addition of non-ionic polymer chains creates an adsorbed layer around the solid particles. As these hydrated layers interpenetrate, they generate repulsive forces, both from the release of water of solvation and the restriction of polymer movement, physically buffering the particles to prevent close approach. This vector diagram maps the thermodynamics of wetting. To successfully disperse a dry powder in water, the liquid must displace air and wet the solid surface. This requires decreasing the contact angle, theta. By using a wetting agent to lower both the liquid vapor and solid-liquid interfacial tensions, the surface free energy drops and the powder smoothly disperses. The state of the particles dictates how the bulk fluid moves. Flocculated suspensions generally exhibit plastic or pseudoplastic flow, meaning their apparent viscosity decreases under shear. Concentrated deflocculated dispersions, however, tend to be dilatant, meaning electrical repulsion causes the particles to rebound under stress, temporarily increasing the system's resistance to flow. The gravity pulling a coarse suspension downward is constant. A stable suspension requires engineering a precise balance between attractive and repulsive forces to actively resist caking until the moment the dose is administered. Emulsions consist of two immiscible liquid phases, usually water and oil, where one is dispersed as fine droplets throughout the other. Coarse emulsions differ greatly from microemulsions, which form spontaneously because co-surfactants drive their interfacial tension down to near zero levels. In a standard emulsion, the massive increase in interfacial free energy created by the dispersed droplets must be overcome by an emulsifying agent. This agent forms a viscoelastic barrier around the droplets. Often, a blend of surfactants is required to build an interfacial film strong enough to physically resist rupture and prevent droplets from coalescing. Emulsions can also be stabilized by finely divided solid particles. The Bancroft rule dictates the outcome. Whichever liquid preferentially wets the solid, meaning it forms a contact angle of less than 90 degrees with the particle, will become the continuous phase. Clays wetted by water form oil and water emulsions, while particles like carbon black, wetted by oil, force water to become the dispersed phase. To select the right surfactant, formulators use the hydrophile-lipophile balance, or HLB scale. It is an empirical metric calculated using the group numbers of a molecule's chemical structure. It assigns a precise value to the surfactant's polarity, dictating whether it will form a highly hydrophilic barrier favoring an oil and water emulsion, or a nonpolar barrier favoring water and oil. If the interfacial film fails, the emulsion cracks, permanently separating into two liquid layers. This occurs if chemically incompatible surfactants are mixed, or if the system undergoes phase inversion, which can be triggered by adding an electrolyte that suppresses ionization, or by simply packing in more than 74% dispersed phase volume. This equation is Stokes' law, and it governs the kinematics of creaming. In a creaming emulsion, density differences force the dispersed droplets to rise to the top or sink to the bottom. According to the equation, the velocity of creaming drops exponentially if you reduce the globule radius squared, A. Velocity also drops if you minimize ρ, the density difference between the two phases. Finally, the denominator relies on eta, the viscosity of the continuous phase. By adding a thickening agent to increase the viscosity, we increase the mechanical resistance of the fluid, slowing the rate of creaming even further. Macroemulsions are intrinsically unstable. Left alone, they will separate. Their functional lifespan is determined entirely by manipulating the specific physical parameters locked within Stokes' law and the HLB scale. Foams represent a coarse dispersion of a gas in a liquid. The gas bubbles are separated by thin liquid films, or lamellae, of colloidal dimensions, which are stabilized by monolayers of adsorbed surface-active molecules. Every foam is thermodynamically unstable due to its massive surface free energy. Instability occurs because of the pressure differential over curved interfaces. The pressure inside a small bubble is mathematically greater than the pressure inside a large one. This forces gas to continuously diffuse out of the small bubbles, rupturing the thin liquid films as the large bubbles expand. To destroy a foam intentionally, we use highly surface-active foam breakers, which locally drop surface tension until the thin regions pull apart and rupture. Alternatively, foam inhibitors rapidly adsorb at the air-water interface to block the foaming agent, but intentionally lack the characteristics to form a stable film themselves. Whether we are analyzing a self-assembling 5-nanometer micelle or the heavy macroscopic flocks of a calamine suspension, the underlying mechanics are identical. Every dispersed system is a battleground of interfacial free energy. Because matter naturally drives toward a state of minimum energy and maximum entropy, the subdivision of phases generates an inherently unstable state. The stability of these formulations relies entirely on actively opposing the laws of thermodynamics. We achieve this by manipulating the entropic drive of hydrophobic surfactant tails, erecting steric barriers with hydrated polymer chains, or utilizing the precise polarity of an emulsifier. Pharmaceutical formulation requires moving past simple mixing. It is a mathematically defined exercise in physical chemistry, requiring the precise calculation of repulsive energies, phase geometries, and bulk fluid kinematics. By perfectly calibrating the interactions at the molecular interface, we dictate the physical reality of the macroscopic system.